Hello, this Bars Lab here. So today we are going to continue doing the series of analysis videos on explosions. It's been a really long time ago since I've done the first explosion analysis video, but now it's finally time to go for number 2 in the series of analysis videos on explosions. So we're going to be looking at this particular experiment. So this person has done also, I have done analysis videos of him on elastic collisions, and now we're gonna watch him doing explosions. So he's using Pascal cards, a red and a blue card, equal masses, and one of the cards is gonna do like 5 runs, and then in each run is going to gradually increase the mass of one card. And then we're going to check the conservation of momentum and the conservation of kinetic energy. So one of the cards, this blue card, has the spring attached to it, which is going to be compressed.
The collisions, but they actually have this spring loaded from here.
It's
very, very sensitive. Press the button, and then that's quite.
Right, so he's going to put the two cards next to each other, and that spring will be compressed, and then he's going to uncompress the spring by pushing a little small button, and then the explosion will occur. So he's going to start off with the same masses, and then he's going to add these bars each time in each run. So he has a table over here with the masses. So each card weighs 270 grams, and the red card is going to remain the same, and then the blue card is going to add masses of 250 grams, I suppose, each time. And then let me show you one example. I'm not going to show you each run. I'm going to show you my calculations. Here we go. Right, that's an example of equal masses. So here is my Excel file with all the calculations. Over here we have the mass of card 1, which remains the same of the red card, and then the mass of the blue card. So 270 grams is the first run. Then we have 520 grams, 770 grams, 1 kilogram and 2 grams, 1 kilogram and 270 grams. Then we have here the velocities. Then we have the momentum. Then we have the momentum, the total amount of momentum when we treat it as a vector, the total amount of momentum when we treat it as a scalar. That's for the alternative model. Then the kinetic energy of card 1, kinetic energy of card 2, and the total kinetic energy combined. So now we're going to check out conservation of momentum. So the basic idea is that the momentum of card 1, of the card going in that direction, and the card going in that direction should always be exactly the same, no matter what the weight is. Well, I mean, the numbers, right? Well, I can show you directly. So for the first run, we have card 1 has a momentum of 0.22 in that direction. The red card and the blue card has also momentum of 0.22. Okay, so those numbers are the same, and that should always be the same. And for the next, when we increase the weight of the blue card, we have 0.27 versus 0.23 going that direction. So it's not exactly the same, but in the next one, it's more the same. You got 0.28 that direction, 0.27 that direction. And then in the next one, 0.29, 0.28. And then in the next one, 0.30, 0.28. So both directions should have the same momentum. And for conventional science, since direction matters, right? When we are going to add these momenta together, one has a positive direction, one has a negative direction. When we combine those momentums, it should add up to 0. So momentum is conserved when the total amount of momentum equals 0 for explosions. No matter what the masses are of the weights, the total amount of momentum after the explosion occurs should always add up to 0. And as you can see here, this is the total amount of momentum. When we treat it as a vector, we see 0.00081, 0.03, 0.01, 0.01, 0.02. So momentum is pretty well conserved here. conserved here. Now, what do we see? We start with momentum of 0.22, 0.22, and then 0.27, 0.23, 0.28, 0.27, 0.29, 0.28, 0.30, 0.28. The momentum are gradually increasing. As the masses are being increased, the momentum is also increasing, which is in contradiction with the alternative model, which says that momentum is energy. There is no difference between momentum and energy. So it is impossible for a spring to produce more energy as we stack more masses on to the carts. But in reality, of course, that's not true. The total amount of energy remains the same, which is the kinetic energy. Because if we go and take a look at the total amount of kinetic energy, we see in each run, so the first one is 0.19 joules, second one is 0.19 joules, third run 0.20 joules, fourth run 0.19 joules, fifth run 0.20 joules. As you can see, the kinetic energy remains the same throughout each run. But for momentum, all right, momentum is slightly increasing in each run. We started with 0.22 and we ended up with 0.30. So momentum is increasing. And for the alternative model, that would mean that the energy is increasing in each run, which means we are dealing with free energy somehow. But of course, that's not true. Momentum is conserved because the direction matters, right? One direction is a positive direction, and the opposite direction is the negative direction. And that's the same for momentum. Positive momentum, negative momentum. Add those together, we have 0 momentum. And in that way, momentum is conserved. If, however, we assume that momentum equals energy, and then, and we treat it as a scalar, that in the sense that direction does not matter, both directions are positive values. We add those together, then we see that in each run, it is being increased. We start with 0.45 for the first run, then with 0.51, then with 0.56, then with 0.57, then with 0.58. We started with 0.45, we ended up with 0.58. So we have extra momentum. If we treat it as a scalar, we are gaining momentum in each run. Free momentum. But the kinetic energy wise, that remains the same. So this is in contradiction with the alternative model's view that momentum equals energy. If we say that momentum equals energy, then we see an increase of energy in each run. And so this experiment basically proves that that there is such a thing as free energy. Once again, for the 100th time, if we assume that momentum equals energy, we are dealing with free momentum, free energy. So just saying that this is in total contradiction with the point of view that momentum equals energy. If, however, if we accept conventional science, right, momentum is that there's a big difference between momentum and energy and kinetic energy, right? That momentum is a vector that direction does matter, then momentum is conserved and kinetic energy is conserved. So there's no problem here. Thanks for watching.